Okay, so here we have part one of our notes. We're going to cover part one and part two, so the gas variables and the minor gas laws here. So first off, pressure is a variable that impacts gases quite often, and pressure is caused by collisions between molecules or atoms and the walls of the container. So pressure is the result of the collision of a particle, which imparts a force, over the area in which that acts. So it is a force per unit area. So if I had my container here, and here's my particle, every time this particle strikes the side of the container, it causes a force against that container, and the area over which it causes that force is a pressure. You can think about a pressure in terms of, you take a shower in the morning, and if you have low water pressure, that means that you're imparting a lower force of that water for every unit area of your head versus a higher water pressure, so a low water pressure here versus a higher water pressure. You're imparting a lot more force over that area, so it feels like you have a nice shower. We have lots of different units that we can measure in. In the United States, we use PSI typically, so that's 14.7 pounds for every square inch is equivalent to an atmosphere of pressure. Otherwise, we have kilopascals, we have millimeters of mercury, we have torr, lots of different units you can use to measure pressure. The next unit that we can talk about is the volume. Again, this is just the space between gaseous atoms or molecules. And so, for example, gases themselves expand to fill their containers. So whatever the size of the container is will indicate the volume of that gas, versus a solid, where a solid does not assume the shape or the volume of its container, so the volume of that solid is only based on the volume of the molecules or atoms themselves. For a gas, again, gases expand to fill the container, so the space of the container is the space of that gas. Certainly, as the particles are bouncing around, we could get that space to widen. So as they move around, the spacing between them can increase. So for example, if I had, it's easiest to judge in a container that is flexible. So if I had a balloon, for example, here's my wonderful balloon. If I have a balloon and I increase the rate at which these particles are moving, I can get the balloon to increase in size. In other words, the space between these particles widens, and the balloon is flexible so that it allows that spacing to widen. We often measure these in milliliters, or we might measure in liters. Certainly in the United States, we have a wide variety of bad units that we would use, like gallons and quarts and things. If you're in the United Kingdom, you might measure it in hogsheads, but we're not there, so we're not going to worry about it. Then, of course, temperature affects properties of a gas. So again, it is proportional to the average kinetic energy of the molecules. So the higher the temperature, the more kinetic energy that they have. This is a constant here. We'll talk more about what that constant is a little bit later, but the relationship is not the temperature equaling the kinetic energy, but rather that they are related to each other, and they're related through this constant, which is Boltzmann's constant. We'll talk about that later. For any gas calculation, we have to be in Kelvin because we want to make sure that the temperature is relating the average kinetic energy, or in other words, proportional to the average kinetic energy. So if we are in Celsius, we could have a 0 degrees Celsius gas, but that doesn't mean that it has 0 kinetic energy. So we want to be in Kelvin, where if I actually was in Kelvin and I had a 0 Kelvin gas, we could say that we have 0 kinetic energy. Okay, then lastly, we have the amount of a gas. We typically talk about the number of particles, not the mass of them when we're discussing gases. So if I have a container that's filled with argon gas, for example, as long as I know that there's 2 argon gas atoms versus a container that has oxygen, where there might be 2 oxygen molecules, these masses would be different. Argon weighs about 40 grams per mole, so 40 grams per mole, whereas oxygen, O2, weighs 32 grams per mole. But we don't care in gases necessarily about the masses, other than the fact that the density of these gases would be different. What we care more about is that there are two particles that are present. So if there are two argon gas particles, they will behave similarly to two oxygen gas particles. They will move and surround and expand in this container, just as we would see the same thing with oxygen. Sorry about the dinging in the background. My apologies. And then let's move on to section 2. So this is, again, how are these variables related? So we have Avogadro's law, which says that the volume and the number of moles are directly proportional. In other words, if I divide those two, I get a constant. We typically have graphed these in the past, where if you graph the volume and the number of particles, you get a nice linear relationship. In other words, that the volume increases as the number of particles increase. Or conversely, as you increase the number of particles, which is typically how we phrase it, then the volume of that container has to increase. Now this implies that the temperature and the pressure are constant. Okay? Otherwise we can't make that statement. And you probably learned back in your chemistry class that if we picked two different points on this line, we would see that the volume at any point divided by the number of moles at any point, which is the slope, would be equal to the volume at the second point divided by its number of particles at the second point. This is Avogadro's law. Let me just do all the ones that are directly proportional again, and then I'll go back to Boyle's law. So Charles' law, the volume and the temperature are directly proportional by the same method. This would be a different K value, but by the same idea, the volume and the temperature will be directly related, and we could do that graph again, but we'd result in the same kind of a relationship, that the volume at any point divided by the temperature at any point is equal to the volume at the second point divided by the temperature at the second point. Again, this is based on that same kind of a graph, where if I graphed volume and temperature, I'd get that straight line, and I'm picking point 1 and point 2 on that graph. Oh, that's supposed to be a 2, my apologies. Dalton's law, pressure and moles, so this is pressure and moles are directly related, same deal. We end up with Dalton's law, P1 over N1 equals P2 over N2. And Gay-Lussac's law, pressure and temperature are directly related. So in this case, P1 over T1 equaling P2 over T2. Again, those minor gas laws. The only one that's different is Boyle's law, which states that they are inversely proportional. In other words, if I multiply them together, I get a constant. The reason that's a little bit different is, again, you can think about this. If you press on a gas, if you put pressure on that gas, the volume of that gas should shrink, assuming that the temperature and the number of particles are constant. And so this graph actually, if I'm doing pressure and volume, is an inversely related graph. So it looks like an inverse. So in this case, the pressure times the volume equals a constant. So if I was picking any 2 points along this line, this is 1 and this is 2, while the slope is not constant, I can say that the multiplication of these two values is a constant. So in other words, the pressure times the volume at point 1, sorry, those are both 1s, has to equal the pressure and the volume multiplied together at point 2. Those two are constant values.